So, good evening and welcome to today's class. I hope my screen is visible and I'm audible to you. So, in the last class, we had discussed about the Bolberry equation um, and what is the Bolberry equation, how it is derived, how is it obtained, and how is it connecting the stomatal conductance to the environmental variables and the photosynthesis, and how this Wahlberg equation is obtained. We tried doing a problem, a simple problem that connects photosynthesis and stomatal conductance, and uh, did the linear regression method to obtain the equation of line that is the best fit between the stomatal conductance and this term called the Ball index. We also get the slope and the intercept values associated with the specific line, which is giving us the sensitivity of stomatal conductance to photosynthesis and the environmental variables, and the intercept is giving us the baseline conductance when photosynthesis is negligible. So the equation is derived to a simple linear regression model where we first find this component or the Bolberry index curve, which is the product of the net photosynthetic rate and the relative humidity at the surface of the leaf divided by the concentration of carbon dioxide on the surface of the leaf. Then using that as an x-axis value and this is the y-axis value, we have a bunch of points which we find the best through the simple linear regression model that calculates using all these equations. We find the line that is best fit to these points, and that the slope and the intercept value. We first looked at how what is the unit of this Bolberry index, which is a unit that is similar to the y-axis, mole per meter square per second, and this is how it is derived. We also looked at the slope value, which is nothing but the difference in the y-axis by the x-axis, which is giving us how much of what is the rate of change of stomatal conductance with respect to the environmental variables and photosynthesis. So this is giving the sensitivity of stomatal conductance to photosynthesis. Basically, as with the increase in photosynthesis, at what rate will the stomatal conductance increase? If the slope is higher, we know that the sensitivity of stomatal conductance to photosynthesis is higher. Same in the case of relative humidity. If it increases at a faster rate, stomatal conductance also will increase. Since the environmental variables, when you consider it for a day's period, the environmental variables are not especially the relative humidity and carbon dioxide concentrations are not going to change extensively. So the only parameter that varies at a rate that is on a daily scale and on an hourly scale is the photosynthesis. So that is why we give more importance to the sensitivity of stomatal conductance to photosynthesis. Now, photosynthesis, as the rate changes, the stomatal conductance also changes in the a quick rate if the slope is higher, and as the slope decreases, the sensitivity is less. In the same way, we found out that the intercept value is giving us the minimum stomatal conductance when photosynthesis will be equal to 0. In a realistic situation, the relative humidity and carbon dioxide concentration is not going to be 0, but the photosynthesis can be 0. And particularly during the night time, when in C3 plus during the night time, photosynthesis is not happening or it is very negligible. Under such conditions, the stomatal conductance is there is still persisting a value of stomatal conductance, which indicates water loss, water leakage, even in the absence of photosynthesis. So this might be a mechanism to maintain the temperature, and this can also give a lot of insight into the water use efficiency of the plant. So one with a higher intercept has lots of water loss as a result of this high intercept value, and one with a lower intercept is water much lesser water slope. Then we looked at how what the stomatal conductance and extension to the boundary layer conductance, and what is the relation between the the total conductance, boundary layer conductance, and stomatal conductance for both carbon dioxide as well as for water. We also looked into two formulas that are used to estimate the concentration of carbon dioxide inside the leaf as well as on the surface of the leaf with the help of the total conductance. And we understand that the relative humidity on the surface of the leaf is not the actual conditions in the atmosphere, but it is the relative humidity on the surface of the leaf ratio of the vapor pressure on the surface of the leaf to the vapor pressure inside the leaf. And so hence we have now talked about stomatal conductance, how it is connected to assimilation and transpiration, how it is connected to um, the environmental variables like carbon dioxide, temperature, and humidity. Now, the next factor that will impact stomatal conductance is soil moisture content. So, before going into that, I would like to show you the run BioPro to see how BioPro is implementing this Bolberry model. So, I'll be moving on to that now. If all of you have it installed in your system, you can go side by side and do it. And if there's any doubt, you can ask me then and there. So I'll just briefly show how we do this in the BioPro model. So, uh, so first I first I take the SAR Studio. So my aim will be to first get the working directory, which is going to be a common destination. So I'll be using the set working directory to choose a directory to run this code on. So I set the working directory to my required destination, and then I will open a new file. The first step is to load the BioPro library, which is basically the BioPro model. And I'll run it. You can either run it using CTRL plus enter, or you can click on this button run to obtain to run a particular line. Now after that, I'm going to see which module in BioPro is going to is dealing with Wahlberry equation. So since there are a lot of modules, I'll use this function get all modules and put BioPro inside two semicolon, two colon marks, and then run this model. I mean, run this function, and I get all the modules that are used that are available in BioPro. So I can see here BioPro Ballberry. So I'll be checking what this BioPro Ballberry is all about. So in order to do that, I will now use the module info function and input this. I copied this Ballberry that is provided in the console over here, and I paste it here between two codes. And if you want me to go slower, please let me know. Um, so after that, when I run this line, I get everything about this model. The module name is BioPro. Yes. Module name is BioPro, These are the input quantities. You need to know the assimilation rate, the atmospheric carbon dioxide, RH. We need to know what are the slope and the intercepts, the boundary layer conductance to water vapor, the leaf temperature, and the air temperature. Now, let's calculate it for some random values to see. And the output we'll get is the carbon dioxide on the surface of concentration of carbon dioxide on the surface of the leaf, and relative humidity on the surface of the leaf, as well as the stomatal conductance. So in order to run this module, we will use the evaluate module function in BioCro, and the module is going to be Ballberry, which is again, I'll copy this over here. Now, when we need to run evaluate module, we need to give the inputs. These are the inputs. So what I'll do is I'll again copy these so that I don't mess up with the uh, name of the inputs. And BioCro requires you to give the inputs in the form of a list. So I'll use this list command and paste all these parameters here. Now we are supposed to give in some value. So net assimilation rate, as you are aware by now, is in the unit of micromoles per meter square per second. So say I'm giving 20 over here. I put a comma. Atmospheric carbon dioxide is in the unit of ppm or micromoles per mole. I'm going to give the current carbon dioxide concentration over here. You need not put any units. You only need to input the number. Now RH, I'm using one value, say 75%. So I'll put it as 0.75. Now B note, let me give the slope as 1.2 and the intercept as say 0.8 or 0.6. GBW, I'll give the total conductance, and this will be in moles per meter square per second. Say I gave 2. The leaf temperature as 28. Now what I didn't do over here is put a comma after all of these. And for the last, which is the temperature of the air, I'll give 32. So these two quantities will be in degrees Celsius. Now, when I run this model, you can see that I get the concentration here 420. Concentration of the carbon dioxide on the surface has been reduced to 406.3. The relative humidity or the humidity at the surface of the leaf is 0.96, whereas we gave a 0.75 value. So this is taking into consideration the boundary layer conductance, and we see the leaf stomatal conductance is 1228.503 moles per meter square per second. If you convert this to millimoles, it will be around 1.23 millimoles per meter square per second of water for this rate of carbon dioxide. So this is how you will run the Ballberry model in BioCro. The inputs will be all of this. So in order to get this V0 and V1, what we usually do is we'll have measurements of AN, and we'll have, when we make measurements of AN, we will also get the measurement of stomatal conductance. Then we will do a linear regression. We'll apply the linear regression to the AN value, the stomatal conductance value. During that time, we have to calculate the carbon dioxide on the surface of the leaf and the relative humidity. So there are a bunch of calculations within this Wahlberry model that will help in obtaining this carbon dioxide at the surface of the leaf using this equation which I had talked about yesterday, this equation. So here we know the boundary layer conductance. We also get the transpiration rate. And all of these input quantities will be put into this equation and CS will be obtained. Same is the condition of relative humidity on the surface of the leaf. Since we have the temperature of the leaf is known, we know the EI value. We just need to give the relative humidity in the atmosphere, and using the boundary layer conductance, they will find out the humidity at the surface of the leaf. So using all of that value, we can run this Wahlberg model to get the linear regression line. When once you get the linear regression line, we can find out accurately for a particular value of photosynthesis what will be the value of stomatal conductors. Now our measurements will be restricted to maybe 10 or 15 values. So we know the value of photosynthesis stomatal conductance corresponding to one particular value of photosynthesis. But when we make an ACI curve, we have like 15 values of carbon dioxide, 15 values of assimilation, 15 values of stomatal conductance. So it is in order to apply that data that we have measured into a standard equation so that we can calculate the stomatal conductance for any value of photosynthesis and relative humidity and carbon dioxide concentration that we develop this Wahlberg parameters and we develop that curve, Wahlberg curve, which is nothing but a straight line. So this is why we are applying or we are finding out the Wahlberg curve. It is to get the value of stomatal conductance irrespective of the carbon dioxide or humidity or photosynthetic rate. What is the stomatal conductance corresponding to that from a bunch of data that we already have. And now in BioCro, Wahlberg is a model. We know that we learned about the FVCB model. So FVCB model is calculating the using FVCB model. BioCro calculates the internal carbon dioxide. So in order to get the internal carbon dioxide, the stomatal conductance is also playing a huge role. So what BioCro has done is BioCro has coupled the FVCB equation and the Wahlberg equation together to form the C3 assimilation equation, which I'll be talking about in the later part of the class. Now, it is for this reason that I have introduced the Wahlberg equation to you, because in BioCro, they are coupling these two modules, the FVCB module and the Wahlberg module, so that those two processes are not simulated separately. We know how both these processes are very interlinked with each other. So the effect of stomatal conductance will be the impact of stomatal conductance can be utilized during the estimation of FVCB parameters, and FVCB also can be impact of FVCB equations or parameters in FVCB model can also be utilized by the Wahlberg equation. This is why those two modules are coupled with each other. Like I said, um, the next parameter that is impacted, now we looked at how the environmental factors are impacting stomatal conductance and how stomatal conductance can be obtained by if we have the environmental parameters. Now stomata is also affected by the amount of water in the soil. This is called the soil moisture content. So if soil moisture content is less, then the water potential between the plant and the roots will also reduce. Why? Because if the soil moisture is less than the water present in the roots, then the gradient of water will be from the plant to the soil, because it will be having higher concentration over here than in the soil. So the plants are not able to take up water. As a result of this, there will be some the leaf water potential. So whatever is the status of pressure of the water outside in the leaf will also reduce. The water potential in the leaf will also reduce. And as a result of it, this is going to affect the opening and closing of the stomata. We had looked at how the potassium ions are going to come out. So when water potential reduces, this also reduces the osmotic potential. Osmotic potential will reduce, then water will come out from the guard cells back into the to the outside of the guard cells. This is going to shrink the stomata. So this is in this phenomenon also needs to be reflected in the stomatal conductance, and this is represented by a a factor called the stomata water stress factor. So stomata water stress factor, when implemented into the photosynthesis and stomatal conductance process, will take care of the reduction in the stomatal conductance as a result of the amount of water in the soil, when the as a impact of the amount of water in the soil. Now, if you consider the soil in the root zone of a plant, when you water it, or when the soil receives a lot of water, the soil in the initial state is filled with water. The soil is in the form of a matrix of pore spaces and soil particles. So the soil particles can be anything. It can be sand particles will be there, silt will be there, loam will be there. There will be gravel particles will be there. So the soil is a complex system, non-homogeneous system that is comprising of a variety of particles. Majorly, we are aware of the organic matter, the sand, soil, sand, clay, loam content, gravel content. And along with that, there are pore spaces between these particles. So when the plant receives or is irrigated or receives a lot of rain, the soil matrix will get saturated with water. But then once it is saturated with water, it cannot hold so much of water in itself. The force, as a result of the force of gravity, some of the water is lost into the water table. It will drain down into the water table. Now, once all this water is drained out into the water table, there is some water still remaining in the pores of the soil as a result of the addition and cohesion between the soil particles. That is, when the soil particles are attracting the water molecules and holding it over there, then that condition with water is called the field capacity of the soil. So the field capacity of the soil is the state in which all of the water that is drained out as a result of gravity goes, and the remaining water stays there as a result of the molecular attraction applied by the soil particles on water. So the soil particles are holding water in the soil. This state where all the gravity water is gone, drained off, and the remaining water is existing as a result of this attraction of soil particle is called the field capacity. Now, this is the best state for the plant. Plant is able to sufficiently take up water when the soil is at its field capacity. When the soil is at the saturated condition also, the plant will not be able to take up all this water that is going to go down as a result of gravity, because the plant also needs to apply some energy to take up the water. So that energy is not as high as the gravitational force. So plants won't be able to take up the gravitational water, but instead the water that is held in the soil, the plant is good enough. It can apply enough energy to take up that water. Now, as time goes, as a result of evaporation or as a result of the plant taking up most of the water, a state reaches when the water in the pores decline, and only water that is called structural water, that is stuck to the soil particles will remain. Now, this water is not available to the plants because the soil particles are attracting the water molecules with great energy, such that the plants are not able to surpass that energy and take that water which is being attracted by the soil. So under such condition where water is not available to the plant is called the wilting point. That where we say that the soil condition is such that it has reached the wilting point. That is because plant cannot take up this water in the soil. Now, the state between the difference of the field capacity and the wilting point, or the quantity of water that is available between this field capacity and the wilting point, is called the plant available water. So, all of the water that is existing or persisting between the field capacity and wilting point is the water that is available to plant. At wilting point, the plant is not capable of taking up water by its roots, and then as a result of unavailability of water, it faces stress and it starts wilting. Now, this water that is available, the water that flows off as a result of the gravitational force is called the gravitational water. In terms of plant, this water is not available to plant because it cannot exert as much force equal to the gravitational force to take up the water. The water that is available to the plant is called the capillary water. This capillary water is existing not only by the intermolecular force or attraction that holds the water in the pore spaces, but it is also existing as a result of the capillary action, which I don't think I need to explain. When you when you dip a tube inside a beaker of water, some water races inside into the tube as a result of the adhesive forces of the glass to the water to the glass. So by this action also, water will be there available to the plants in the soil, as and also the intermolecular forces of soil will hold some water in the pores of the soil. So that water is called the capillary water. Now hygroscopic water is the water available in the soil at the wilting point. Hygroscopic water is not something the plant is able to take. We have to in order to obtain the hygroscopic water, we have to take the soil and dry it in the oven up to some degree of temperature, and only then that water can be removed, water can be separated from the soil. Otherwise, that water is not available to plants, or that water cannot flow away, or that water does not drain out as a result of gravity. It is also called structural water because it is stuck to the soil particles, and soil is attracting it and keeping it to itself with so much of energy that a lot of energy, like high heat conditions, are required to break the bond between soil and water. Now, this field capacity and wilting point that I'm talking about, what is it actually? So, field capacity is nothing but the soil volumetric water content or soil moisture content expressed in percentage of total available water. So it is a fraction, it's a fraction quantity, or it is a percentage. Uh, um, it is expressed in terms of a percentage, which is the fraction of water per unit of the soil available. So we know that in sandy soils, the particles are a little bit bigger. And because of that, there are a lot of pore spaces in sandy soil. If you see, if you go to the beach and all, if you pour water into the sand, it goes off quickly. It will seep down quickly. That is because in a matrix of sandy soil, there are a lot of pore spaces. As a result of it, water will flow down quickly. Now, at the same time, if when you come to clayey soils, the particles are even smaller. So as a result of which, the pore spaces are also very tiny. And because of this, the water will not move very quickly as easily as in sandy soil. So the field capacity in case of the sandy soil is going to be low because all of the water is going to go off as gravitational water. Clay soil, the field capacity is going to be a little more higher because the soil is able to retain some water because the pore spaces are very tiny, and the capability of the water to flow off very easily is less in terms of clayey soil. And again, when it comes to loamy soil, it's a mixture of sand, silt, and clay. So it has got a little more um, a good amount of field capacity because it's a mixture of sand, silt, clay, all different particles. So it is also not able to drain off the water as easily as sandy soil. So it can retain some good amount of water, which is why it is called ideal for plants. Now, not only are the pore spaces a factor of the types of soil, the organic matter in the soil, how the soil structure is. Sometimes the soil particles are with sharp edges. Sometimes the soil particles are rounded. Sometimes it forms a honeycomb structure. Sometimes it forms a stratified structure. So those structural composition or structural structure of this soil also impacts the field capacity as well as the wilting point, and amount of organic matter present in it affect the field capacity. How well it is compacted, or if the soil is loose, then again the field capacity vary based on all of this. So field capacity is nothing but it is the it is the volumetric soil water content. Nothing but when you take, say, when you take 1 meter cube of soil and you obtain the water that is present in the soil like this. Now, say if this is one whole total soil volume, and you see that the soil has got some air spaces also, the soil has got water also available. So when you estimate, when you take out the entire water that is available in the soil and divide it by the total volume of the soil, then the quantity, that fraction you get, is called the soil water content. Now, soil water content at this field capacity is called the field capacity, and soil volumetric water content at wilting point is called the wilting point. Now, in this water content can be expressed not only as the quantity of volume but also as its mass in terms of its pressure and everything. But since we will be majorly using volumetric water content, I'll be only talking about that. In order to measure the field capacity and the wilting point, definitely what we'll have to do is measure how much of soil water is available. So that can be done through a variety of methods. In laboratory, there are instruments called pressure plate apparatus and tengiometers that measures, a tengiometer measures the metric potential in of the soil. Pressure plate apparatus is again something corresponding to the pressure. In field, there are gravimetric methods where the soil is collected and it is oven dried. So you get the mass of the total soil. You get the mass of the water. When you oven dry it, all the water evaporates. So you will get the mass of the water available, and from that you can divide and get the um, gravimetric volumetric content, or soil, not volumetric, gravimetric method, we'll get the soil water content. Then there are soil moisture sensors that works on the principles of capacitance and um, time domain reflectometry, where two rods are inserted into the soil, and when electric currents are passed, based on the time delay in the response that is reaching the other electrode, we can estimate what is the water content in the soil. So in the end of the day, it is all the water content or the fraction of the water content that is obtained. And we will be using the volumetric water content. Soil volumetric water content is nothing but the volume of the water present in that total volume of the soil. Now, in order, we are talking so much about the volumetric, um, field capacity and wilting point, and the soil water content, because we want to find out what is this presence of soil moisture, how is it going to affect the stomatal conductance. So we translate the soil water content into some factor called the stomata water stress factor, where again there is a linear model that is associating the stomata water stress. This is stomata water stress, and the y-axis is stomata water stress, and the x-axis is the soil water content. So soil water content, when I say soil water content, it is soil volumetric water content. And now, in order to find what is the soil volumetric water content at field capacity and wilting point, there are a lot of empirical equations like the Mann-Genekten model, there is some Rawls model, Saxton's model. So all of this helps in estimating the soil water content at based on the amount of sand, amount of silt, amount of clay, amount of organic matter, etc. Now, after obtaining the soil water content, after applying what is the amount of sand, say we have in when you take a volume of sand, 21 percentage is 21 percentage of the soil is, say, sand. Then we have 60 percentage, we have clay, and the remaining percentage silt. Then based on all of these percentages, we can find out what is the soil volumetric water content. Now, the soil volumetric water content at The water content at 1500 kPa is the volumetric water content for wilting point, and the one at 33 kPa is the water content at field capacity. So if we know that the field capacity is attained when the potential of water there is at 33 kilopascals, and the wilting point is at the metric potential or the suction pressure or the pressure head is at 1500 kilopascal. So if we know the if we know the formula, we can find out what is the soil water content corresponding to this pressure values. Then we will get the volumetric water content at field capacity and volumetric water content at wilting point. Now all of these are again a lot of equations which we don't need very extensively, because we just need to find out what is the stomatal water stress and how the stomatal water stress is varying with the soil water content. So in this linear model, what you see is at wilting point over here, the stomatal water stress will be 0. And then as it moves to the field capacity, suppose this will be the third, okay, this is the soil water content at 1500 kilopascal, and this is the soil water content at 33 kilopascal. So as it reaches the field capacity, we see that the stomatal water stress is 1. Now, what does stomatal water stress equal to 0 mean? Stomatal water stress is equal to 0 means the stress is very high. And if stomatal water stress is equal to 1, it means the stress is, there is no stress. There is no stress on the stomata as a result of soil water, as a result of moisture content. But if the stomatal water stress is 0, it means that uh, the stomata is affected heavily as a result of the soil moisture content. So this linear model will give us a stomatal water stress factor that is connecting the stomatal conductance and the response of it to the soil water content. We are using a linear model. Again, here we have to find the slope of this line. So in order to find the slope of this line, we do this again, delta y by delta x. So at field capacity, we know that y is equal to 1. And at a wilting point, we know that y is equal to 0. So 1 minus 0 divided by the volumetric water content at field capacity minus volumetric water content at wilting point will give us the slope. Nothing, it is just again delta y by delta x is equal to slope. So this, since we know that the y value at this point is 1 and y value at this point is 0, we will take this delta y as 1 minus 0 and delta x as theta fc minus theta wp. From that, we will get the slope. Now, in order to find the stomata water stress, which is again nothing but an equation of this line. So, equation of the line is equal to, say, y is equal to mx plus c. Y is equal to mx plus c. We found out that the slope is equal to 1 minus theta fc minus theta wp. Now, plus c. Now, in order in order to find out what is the intercept value, we know that the intercept yeah, y is equal to 1. At y is equal to 1, x is equal to theta fc, right? At y is equal to 1, x is equal to theta fc. This is the slope value and this is the intercept value. So in order to get the intercept, we'll do 1 minus theta fc by theta fc minus theta wp. Fc minus theta wp. So from this, we know this term is equal to 1 minus slope into theta fc. So this will give us the intercept value, which is nothing but this 1 minus theta fc into slope is the intercept value. So this is how you get the intercept value. Now applying this and this in this y is equal to mx plus c, we get m is equal to 1 by 1 by theta Fc minus theta Wp. This is water stress. X is again some soil water content that we don't know. And the intercept is minus 1 plus slope into theta Fc. Now, after the substitution, when you rearrange the terms, finally you will get the equation as theta minus theta Wp divided by theta Fc minus theta Wp is equal to the stomata water stress. So this is the same thing that we learned yesterday with regard to the linear regression model. You need to find the slope, you need to find the intercept, and then you need to substitute in the equation of the line. Then finally you will get this equation, which is the equation to find out the stomata water stress. So if we have the value of the soil water content, if we have the value of the wilting point, and if we have the value of the field capacity, we can find out the stomata water stress factor. Now, I just a second. I would like you to do a problem here to find out. Okay, I think yeah. So please find out the stomata water stress for theta Fc is equal to, very simple problem, just so that you can, theta Fc is equal to 0.25, theta Wp is equal to 0.15, and theta is equal to 0.18. Find out the stomata water stress for these conditions. So the equation for stomata water stress is theta minus theta Wp by theta Fc minus theta Wp. Please do it so that this is very simple arithmetic, because I want you to take you to what is the extent of the stomata water stress that you will get. So if you do this problem, you will have an idea as to what I'm going to be explaining later on. So try to do this. Yeah, right, Haritha, your answer is right. Ananta, just look at the formula once more and yes, please put in your answer. I'll take a 2-minute break and get back to you. By that time, you can drop in your answers in the chat box. Yes, all of your answers is right. It's 0.3. So now we know that theta minus theta FC by theta FC minus theta WP will give you 0.3. Now, at field capacity, what will this be? Just try at field capacity. Suppose if our soil has got water content equal to the water content at field capacity, then this theta value is going to be 0.25 minus theta WP, not theta FC. I'm sorry, this is theta WP, not theta FC. Theta WP. Here also theta WP. So theta minus theta WP will be equal to 0.1. Again, the denominator is also going to be the same. So the stomata water stress is equal to 1. And then at wilting point, suppose our soil water content is at wilting point, then the soil volumetric water content is equal to the stomata water stress factor is equal to 0. So this is why we see here any value of water content that is below, suppose this is the wilting point and this is the field capacity. So any value, say if you have 0.27 or 0.3 or 2 or whatever it is, the stomata water stress is going to be equal to 1 for all the values that are higher than 0.25. And if the water content is anything less than 0.15, then all of the values are going to be 0. So the stomata water stress is one factor that is extending between 0 and 1, where when the water content is at field at wilting point, stomata water stress will be 0. Anything less than that will be 0. In between this, it will be any value between 0 and 1. At field capacity, it will become equal to 1. And as it extends over there, it is also going to be equal to 1. So, stomata water stress factor will always be between 0 and 1. So, again, I'm going to apply this thing in the how do I apply this in Biocro? I go back here to see if there is any stomata water stress module. And then I see here there is a stomata water stress module linear. So I will take this and then I will go module info and this. And when I enter, I get the input, output, and all the quantities required for that. The module input quantities are soil field capacity, soil wilting point, soil water content, and output you will get the stomata water stress. So again, just now we did a problem. I'm going to do the same problem with this Biocro, this module over here, which is nothing but this linear model. Now I have to put the input quantities as soil field capacity, which is equal to 0.25 is the value we took in the problem. Then the wilting point is equal to 0.15, comma, and the soil water content is equal to 0.18. So when we run this module, it has to be a comma. I put a full stop over there instead of a comma, so that is where that error came. Now I'll run it and see I get the stomata water stress as 0.3. So basically this module is not doing nothing, but it is using a linear model to estimate the stomata water stress by finding the slope and intercept. So as simple as this is what the module is about. Now, since we know what is the theory behind it, we can itself create a module like this in Excel or using any programming language and estimate the stomata water stress. So now we looked at two factors that are impacting the stomatal conductance. One is the environmental factors, and the other is the soil moisture content. Now the third part, I think I'll cover it towards the end. But right now, since we already found out a way to now same like soil moisture content, the abscisic acid is also going to impact the stomata. So for that, there is a module that estimates the stomatal water stress as a result of abscisic acid. I'll go into that later on, but as of now, we know one method to estimate the soil water, the stomata water stress. Now, why I need all of this is because, like I said, there is a module in BioCro that combines, that couples the FVCB module and the Ballberry module. Now that module is called the C3 assimilation module. So if you go here, we see that, okay, there is one module called the C3 assimilation module. So I want information regarding this module. So I do module info and paste this, and I run this, and I see that in the module, we have a lot of input quantities like these and output quantities like these. Let's see what these input and output quantities are. So the input quantity is nothing but QAbs, which is nothing but the incident photosynthetic photon flux density, which is nothing but the incident light that is available to the leaf. Then the temperature of the leaf, the air temperature, relative humidity. Vmax1 we know it is a maximum rate of carboxylation. This is the maximum rate of electron transport. This is the maximum rate of triose phosphate utilization, the dark respiration rate, the Ballberry intercept and the slope, minimum stomatal conductance. Now this value is nothing but stomata will never go to the value of 0. There will be a very minimal value like point. So in order to, we don't want to make the stomata as 0. So in order to include some value, some basic value, the module takes a minimum stomatal conductance as 0.001, which is equal to 0, negligible. But then again, since for the purpose of coding, we don't want to use the 0 value. So there we use one minimum stomatal conductance value of 0.001 or 0.0001 or anything except some value that is slightly more than 0. Then we have to input the atmospheric carbon dioxide. We have to give in the atmospheric pressure, oxygen value. Theta value is the convectivity factor. Again, in the AQ curve, there is a time when the slope will transition to asymptote, and that factor is called the convexity factor. Stomata water stress, we just now looked. It is a factor that takes into consideration the stress on the stomatal conductance as a result of soil moisture. Electrons per carboxylation, we know it is a value that is used in the RUBP regeneration limited photosynthetic rate, and electrons per oxygenation also. Beta psi is nothing but the fraction of incident light that is available to photosystem 2. GBW is the boundary layer conductance. So now when we have all of these value, what this module does is it not only it can take the input of ACI AQ curve and also the stomatal conductance and give us the stomatal conductance value, which will be used in the FVCB equations, which will again give us a more reliable value of the photosynthetic rate. So here we get the net assimilation rate, we get the stomatal conductance. Like I said, assimilation, when we do an ACI curve, we have the net assimilation rate to different values of carbon dioxide. So in order to get a final assimilation rate of that leaf, we have to make use of all those equations, find the minimum value, and then we have to estimate it. Then the stomatal conductance also. We also get the carbon dioxide on the surface and the relative humidity on the surface. We get the intercellular leaf carbon dioxide concentration, the gross assimilation, the assimilation that is limited by conductance, the rate of photorespirations. So all of these output quantities can be obtained if we given the inputs of ACI and AQ curve. So in order to run this module, we are using the FVCB equation and the Ballberry equation. So in the next class, this will be the end of today's class. In the next class, I'll be running this examples of ACI and AQ curves using this C3 assimilation module. And yeah, seeing how this application may be used in real-time studies for finding the rate of photosynthesis and rate of photorespiration and everything. So that will be the end of today's class. If you have any doubt, you can ask me now. Otherwise, you're free to leave the session. Thank you for attending today's session.